All right, we are going to get started with the 6-7 notes, and this is a big lesson. I hope you guys enjoyed your snow day. But this lesson is really like the kind of the opposite of the power rule. So the power rule when we did derivatives was like this super important lesson where we learned kind of the key for how to take the derivative. And today we are going to talk about how to find the antiderivative or the integral. Okay, so the antiderivative of a function little f of x is a function big F of x. And we've talked about this before where the antiderivative or the integral of little f is big F. Okay, so if I took the derivative of big F, right, big F prime of x is little f of x, right? The derivative of big F is little f. Kind of feel like an elementary school teacher with the big F and little f. I don't know why this is the notation, but it is the way it is, I suppose. Okay, so let's kind of talk about the antiderivative. So, for example, let f of x be 3x squared, and then f prime of x is 6x. So the derivative of 3x squared is 6x, which means that 3x squared is the antiderivative of 6x. Why is that? Well, we're just going the opposite direction, essentially. So we're trying to figure out what function would have its derivative be the thing that we're looking at. So we're going the opposite way. When we take an integral, it is taking the antiderivative of a function. The area under the curve is represented by the antiderivative, which is kind of crazy. So being able to take the antiderivative is going to allow us to find the exact area under the curve. The exact area under the curve. No more needing to do Riemann sums. You won't have to do like, okay, this is the area of a semicircle plus the area of a triangle plus the area of a rectangle. We can actually find the exact area under any curve. It's kind of crazy. Okay, so let's kind of review the power rule for finding a derivative. So this is something we talked about way back in Unit 2. So if my original function is x to some power n, right? N is just a constant. What do? We multiply, n. That's an n. That coefficient to the front, and then we subtract 1 from the exponent. So the derivative is n times x to the n minus 1. Like, for example, if I have x to the 5th, the derivative of x to the 5th, I put 5 in front, and then I decrease the exponent by 1, and that's our power rule. So this is the generic rule here. Now, antiderivative, we just undo everything that we did before. So we go backwards. What's the opposite of subtracting 1 from the exponent? Step 1 is to add 1 to the exponent. We add 1 to the exponent, and then I need to do the opposite of multiplying by the old exponent, which is to divide by the new exponent. Okay, so let's use this to find the antiderivative of x to the n. So we add 1 to the exponent, which gives me x to the n plus 1. And then we divide by that new exponent. So divided by whatever n plus 1 is. Now, this notation looks kind of funky because all the n's and plus ones and everything. But as soon as we do some actual examples, I think it'll really start to click. So, given the function little f of x, find the antiderivative big F of x. So here we have x squared, and I want to find the antiderivative. So we're going to do the power rule in reverse. So step 1 is to add 1 to the new exponent. So big F of x. We're now going to have x cubed. And then we divide by that new exponent. So divided by 3. Or if you wanted to write it like this, we could as well. Now, another thing that I'm going to do is I'm going to add a plus c. Okay, c is a constant. Now, I know we haven't really talked about this at all, but one thing to think about is if I took the derivative of big F of x, I should get little f of x. So let's think about it. If I multiply by 3 and then decrease the exponent by 1, I will in fact end up with x squared. The reason why we put a constant on the end is because I could have any number added to the end of this function and x squared would still be its derivative, right? So if I have 1/3 x cubed plus 3 or 1/3 x cubed plus 7, 1/3 x cubed minus 4, when I take the derivative, that constant goes away. So this would be our antiderivative here. Okay. Before we do this, I am going to rewrite this. 6 over x cubed is 6 times x to the negative third. So we're going to apply our power, or the antiderivative of the power rule. So we have to add 1 to every exponent and then divide by the new exponent. So I'm going to have big F of x, increase the exponent by 1, and then divide by it. Same thing again. Increase the exponent by 1 and divide by it. Now, how would I do the antiderivative here? Well, kind of what I think about is, okay, what has a derivative of minus 1? Well, it's just minus x, right? If I take the derivative of minus x, I get minus 1. And then I'm going to add that plus c. Now, we can kind of clean this up a little bit. I'm going to have big F of x equals 5/4 x to the 4th. 6 divided by negative 2 is just negative 3, so I'm going to have minus 3 over x squared. I can flip that negative exponent back down to the bottom. Minus x plus that constant c. So again, if I took the derivative of big F of x, I should end up with little f of x. All right, let's try this one. Again, I'm going to rewrite this. Square root of x is x to the 1/2. This is 3 times x to the negative 1/2. Okay, we keep applying the same rules here. Add 1 to the exponent and then divide by the new exponent. So big F of x, I'm going to add 1, which gives me 3/2, and then I divide by 3/2. Plus 3 times x to the positive 1/2 divided by 1/2. Okay, so dividing by 3/2 is the same thing as multiplying by 2/3. Oops, there's an equal sign in there. 2/3 x to the 3/2. Dividing by 1/2 is the same thing as multiplying by 2. So I have 6, because 3 times 2, and then x to the 1/2 is just going to be the square root of x. And then I'm going to put that constant on the end there. All right. Let's talk about sine and cosine integrals. So again, we kind of have to think about what is the antiderivative? What function, when I take the derivative of it, will give me sine? So I know that the derivative of cosine is negative sine. So if I want the derivative to just be sine, that means I need the function to be negative cosine. And then I'm going to put that plus c there. So the antiderivative of sine is negative cosine. The integral of cosine, and this is just going to be sine, because if I take the derivative of sine, I get cosine. Okay, now here is our big rule, and this is huge for understanding integrals. The fundamental theorem of calculus. It's called the fundamental theorem of calculus. So, if f is a continuous function on a closed interval, then the area under the curve from A to B can be represented by this. So this is notation that we're familiar with, right? We're finding the area under some curve, f of x, from A to B. And this is what it is. It is big F of B minus big F of A, where big F of x is the antiderivative of little f. Isn't that so crazy? So we find the antiderivative of whatever little f of x is, and then we plug in those endpoints and subtract them, and that's going to give us the exact area under the curve. It's wild. All right, let's do your first real integral. I'm sad we can't be together for this, but we'll do more integrals tomorrow. Okay, evaluate the definite integral. Use a calculator to check your answer. And I'll show you how we can use a calculator. Well, I guess we did do that, didn't we? We'll use that again. Okay, so we have to find the antiderivative. So we're going to use our reverse power rule here. So if I do the antiderivative of 4, I get 4x. And kind of my mental check again is if I take the derivative of 4x, I get 4. So that's how I know I'm on the right track. All right, I'm going to increase my exponent by 1 and divide by that new exponent. So this is our antiderivative. And I'm going to put this line here with a 5 on top and a negative 2 on the bottom. So this is kind of the notation that you'll see where it's like, okay, I know I still have to plug in 5 and negative 2 into this because like we talked about in the theorem here, I have to take the antiderivative, but then I have to plug those numbers in. Okay, so this is really just 3, right? So I'm going to plug in 5. So I'm going to have 4 times 5 minus 3 times 5 squared, and I'm going to put big brackets around that. And this is just a matter of, keeping your work organized. Keeping your work organized and easy to read. For me, for you, and eventually for whoever is going to be grading your AP exam. If you have organized, easy to read work, it's going to be a lot better. All right, so I plugged in 5, and now I'm going to plug in negative 2. So I'm going to put a new bracket. So I'm going to have 4 times negative 2 minus 3 times negative 2 squared. Okay, so that gives me 20 minus 5 squared is 25 times 3 is 75 minus, that's negative 8 minus 12. So what is that? Negative 55 minus negative 20. So plus 20 gives me negative 35. So let me go grab my calculator real quick and we will check this. So last Thursday, isn't that crazy? It's been a whole week. Last Thursday, I showed you guys how to do Math 9. Math 9. So let's double check that we get the same thing here. Negative 2 to 5 of 4 minus 6x. Now this is just a line. It's a linear function. So if we wanted to, we could calculate the area under the curve because it's going to be some sort of triangle or rectangle and triangle trapezoid kind of shape. Oh, I don't want to graph it. And there we go. We get negative 35. Okay. Let's try this one here. Okay. We got to do the antiderivative. So first of all, I'm going to rewrite this. Square root of x is x to the 1/2. And this is x to the negative 2. All right, so we're going to do the antiderivative. So we're going to add 1 to the exponent and divide by it. Minus x to the negative 1 divided by negative 1. And I have to take this and I have to plug in 4 and 1. All right, I'm just going to clean this up a little bit. So I have 2/3 x to the 3/2. Those negatives become a positive plus 1 over x. All right, so I have to plug in 4 and 1. So I have 2/3 times 4 to the 3/2 plus 1/4 minus, now I have to plug in 1. 2/3 times 1 to the 3/2 plus 1 over 1 is just 1. All right, 4 to the 3/2. Square root of 4 is 2, and 2 cubed is 8. So that's really an 8. 2 times 8 is 16. So I have 16 over 3 minus 1 to any power is just 1. We like that. So this is 2/3 plus 1. All right, if I get a common denominator here, what are we going to have? Times 4 is 64 over 12 and 3/12. So we have 67 over 12. That is 5/3. And 5/3 is the same thing as 20/12. So 57/12 would be the area under this curve. All right, hopefully I did my fraction math correctly. Just kind of trying to do it quickly. Math 9, 1 to 4, square root of x minus 1 divided by x squared dx. Moment of truth here. All right, let's check. 57 divided by 12. Okay, did something wrong. All right, let me figure it out here. Oh, well, apparently I can't do subtraction. 67 minus 20 turns out is actually 47. Who would have thought? And 47/12 does, in fact, match the right answer. Little rusty after a few days off here, I guess. All right, almost there, guys. So we have the integral from 0 to pi over 2 of 4 sine x dx. Now, one of the things to remember, and we talked about this last week, is that if I have a constant at the front, I can actually move it to the outside of the integral and kind of just ignore it and not worry about it. You don't have to, but sometimes it's nice to just kind of leave it on the outside, and then what you're going to do is multiply your final answer by 4 at the end. So we'll just do it that way. Now, we talked about the antiderivative of sine is negative cosine. So I'm going to have 4 negative cosine evaluated from 0 to pi over 2. So I'm going to have 4 times negative cosine of pi over 2 minus negative cosine, so plus cosine of 0. Okay, cosine of pi over 2 is 0. Cosine of 0 is 1. So we have 4 times 1, which is 4. All right, so let's see if I did this one right here. Math 9, 0, pi over 2, 4 sine x dx 4. So again, what are we finding? We're finding the area under this sine curve, or we're finding the area under this crazy square root of x minus 1 over x squared. All by just finding the antiderivative, which doesn't really seem intuitive, but it's really wild that this is the way it works. Okay, so f prime of x equals x squared minus 2, and f of 1 equals negative 2, then f of 3 equals what? Okay, so this has to do with understanding the fundamental theorem of calculus a little bit, and the fact that the antiderivative, or the integral, is an accumulation function. So here's what we're going to do. F of 3 is equal to f of 1 plus the integral from 1 to 3 of f prime of x dx. All right, so let's kind of digest what this means here. The integral of the derivative, this is an accumulation of change. Accumulation of change. So this is telling me how much f of x is changing from 1 to 3. So I'm starting at f of 1, and then I'm adding a certain amount or subtracting a certain amount. I'm changing, right? There's an accumulation of change, either positive or negative, from 1 to 3, and I'm going to end up at f of 3. Another way to think about it is it's just kind of a rearrangement of the fundamental theorem of calculus. If I move this f of 1 over to the other side, I would have f of 3 minus f of 1 equals the antiderivative, which is exactly what this is. So it's just kind of rearranging that in a way. So let's actually figure this out. So we have f of 1, which is negative 2, plus the integral from 1 to 3 of x squared minus 2 dx. So we have negative 2. All right, my antiderivative, I'm going to add plus. I'm going to add to 1 to the exponent and divide by it. That's going to be minus 2x. And then I have to evaluate that from 1 to 3. So negative 2 plus, I'm going to plug in 3. 3 cubed minus, or over 3, minus 2 times 3. Minus, plug in 1. 1 cubed is just 1. Minus 2 times 1 is just 2. All right, 3 cubed is 27. Over 3 is 9. Run out of room. Negative 2 plus 9 minus 6 minus 1/3 plus 2. All right, those cancel out there. And that's just 3 minus 1/3. So that's going to give me 8/3. So f of 3 is 8/3. All right, guys, that is it for the video. If you could also try the problems on page 37, so 1 through 8 on page 37, and then we will talk about it tomorrow.